A big thank you to all my patrons who support the Engineered Mind podcast. Hi and welcome to the Engineered Mind podcast episode 61. In this podcast we cover topics such as engineering, AI, neuroscience, life, and other interesting topics and fascinating ideas to educate, inspire, and engineer people's minds all around the world. I'm your host Joseph, and for this episode of the podcast, I am very delighted to welcome Sanjay Choudhry to my show. Sanjay is a senior director at NVIDIA with a strong background in both traditional computational methods as well as machine learning in science and engineering. He leads the engineering efforts on SimNet and is passionate about development of AI-based simulation solutions for industrial applications. NVIDIA SimNet is a physics-informed neural network, short PIN, toolkit for engineers, scientists, students, and researchers who either want to get started with AI-driven physics simulations or would like to leverage a powerful framework to implement their domain knowledge to solve complex nonlinear physics problems with real-world applications. In this very exciting podcast, we covered AI in the field of simulation and CAE, data-driven solutions and networks, physics-informed neural networks, SimNet, tips on how you get started with SimNet, and much more. For updates on upcoming podcasts, projects, and videos, make sure to follow me on Twitter as well as on Instagram. To join my weekly newsletter, engineeredmind.sh, where I share exclusive content, visit yusuf.substack.com. And now, ladies and gentlemen, here's my podcast with Sanjay Choudhry. Hey Sanjay, welcome to my show.
It's a pleasure to be here, Joseph.
Excellent. So today we want to talk about the AI simulation toolkit, namely SimNet from NVIDIA. But before we jump into that, I think the audience is very well interested in who is Sanjay, what does he actually work for or at NVIDIA, and what did you do before? Because you have quite a lot of experience, I would say.
Thanks. Yes, I'm in the software group at NVIDIA, leading the charge on SimNet. Which is a neural solver, and we'll go into more details a little bit later. My background is in computational techniques, machine learning, and AI in visualization. So this is a perfect opportunity to make a big difference in the world of simulations.
Great. So let us start by talking a bit about how simulation actually changed over time. So in the past, it was predominantly by prototypes. So we had plenty of prototypes, less of simulation. And then today we have more simulation, less prototypes, moving into the future, more into the data-driven approach. Could you give us, like, from a timeline perspective, kind of where we have been, where we are now, and where we are heading towards?
Right. Clearly, in 60s, basically, and even a good part of 70s, product design, development, manufacturing actually relied on prototype development, experimentation, and that had its own limitations. The cost was very high. The time to develop basically, and the time to market was high, and product quality was not necessarily as good, and the products were over designed or not optimized. That was in the digital. Then came the digital design and manufacturing, basically, where a lot of these simulation codes got developed. And in other areas of engineering as well, there was a simultaneous development of numerical techniques for simulating other kind of events as well, besides design and manufacturing. And that continued for a few decades until recently. When AI actually and machine learning have come in a big way, and they were there before, but what has made them possible now is the power of GPU, basically in extreme parallelism, and it is exactly because of that that clearly the research effort actually towards development of algorithms has increased. AI has taken a little different route in science and engineering, or I should say it's a little bit slower than other areas, partly because of availability of data. And the other reason is because of the laws of science, basically, which need to be obeyed and respected. So clearly, in terms of the evolution, the first thing to do, which was a natural thing to do, was to take the already existing developed techniques and networks and apply them to the problems in science and engineering, which basically means data-driven networks. That they still are very, very popular. In fact, probably dominate the field even now. However, these kind of networks have their own limitations, basically, which we'll discuss. And there, after that came the physics-based networks, basically. The pioneering group for that was Professor Kanadakis at Brown University, and many, many more actually researchers after that have developed different flavors of physics informed, physics constrained, or physics driven, whatever lingo one wants to use, neural networks, basically. They all differ in some ways, but nevertheless, the idea is the same, that physics drives the problem, just like in traditional solvers, except that neural networks advantages, basically, that inherently are present, get leveraged.
Mm-hmm. Makes absolute sense. Thank you so much for the insight, Sanjay. When we talk about neural networks, of course, the term AI comes up. Could you give us like an overview for the audience who is not familiar with AI? What can we actually do with AI in terms of simulating computational physics, computational engineering? What else can we do with AI?
So AI practically pervades all areas of our life now. And that's what NVIDIA's mission is, basically. As you can see, it has been used very successfully in autonomous vehicles, autonomous machines, robotics, etc., smart cities, healthcare, of course, image processing, text and speech, and those are sort of well within sort of the reach of AI. And in fact, most of the earliest algorithms basically were developed for those kind of problems. Businesses started using machine learning to get trends and basically get the hidden information or information hidden behind the data. And I think recently, well, a few years back, it has started coming in the domain of science and engineering as well. And there the field is vast open, because not only one talks about, when we talk about these kind of networks, they are in physics, although primarily our focus is that, but even computational biology, computational chemistry, geophysics, and many other areas basically have seen development of neural networks to solve these kind of problems in science and engineering. And not only just solve the problems, but also solve them in a way that cannot be solved by the traditional methods today. And also be applied in areas where traditional solvers don't even exist today. And we'll discuss some of those as well in this session.
Yeah. When it comes to AI, a lot of people have this strong coupling in mind that AI needs a lot of data. Could you give us like the data versus physics framework? Because there are some terms which I think should clarify, things like forward solution, inverse solution, and the data-driven solution. Could you clarify this for us, maybe, Sanjay?
Sure. So I think data actually was plentiful in many domains. Like, as I said, image processing, natural language processing, and other basically areas where there's a streaming data, or there's plenty of data already that exists. You don't have to generate a new one. Even in medical imaging, for that matter. And these were very successful in bringing AI to the level which could be trusted. Case in point in healthcare is where, for example, you have dermatopathologists basically who are reading slides, and essentially that task can be sort of taken over by AI in a way that leads to standardization of such readings, basically. But such advantages don't necessarily occur in science and engineering problems. When you're trying to solve the problem, you have to obey the laws of physics, laws of science, whatever the scientific problem one might be solving. And therefore, this whole class of basically science, and I say science-driven more than physics-driven, because there are other areas as well in engineering problems where typical data-driven networks have their shortcomings, because data is, first of all, very, very hard to generate. You can't get in as much as you can in other areas, but even the ones that you can generate takes a lot of time. And thirdly, not necessarily checking on the laws of physics or laws of science basically being obeyed necessarily leaves a little bit of uneasy feeling whether the fidelity of the solution predicted by the neural network is going to be satisfactory. All those things actually have led to these kind of networks, and that's what I think the world will see more and more going into the future. And I'm truly excited that AI basically will revolutionize the field of simulations, just as it has in many other areas.
Yeah. Could you maybe for the audience give like one or two examples when it comes to the forward solution, the inverse solution, and the data-driven solution? What did you have in mind as a use case, for example?
Yeah. So one can see a whole spectrum basically of solutions as forward, inverse, and in the middle. So the forward solution is typically what you see with the traditional solvers. All you have is just a description of the problem. You know what kind of physics, let's say, will be behind it. And just like the traditional numerical solvers, basically, AI would solve it in the same way. Inverse problems basically become more interesting, which typical numerical solvers don't address. Those basically could be where you know the end state completely, but you're trying to decipher, for example, coefficients of PDE, just as an example. That clearly is not within the reach of, or at least it doesn't exist in most traditional solvers. Somewhere in the middle is the data simulation methods. And I say in the middle because while you have all the data that you want in the inverse method, and you have the complete solution problem description basically in the forward method, the data simulation methods would work with both physics and data. It could, for example, the problem of medical imaging where you have 4D data from 4D CT scans or MRIs, but you don't know the underlying physics of a blood flow, for example, in the blood vessels. That clearly falls in this class of problems. So those are various ways basically that one can actually look at the problems. Even in the forward solution, I would say the traditional solvers, while they can solve the problem, speed is always a main consideration. Or the number of simulations that one can conduct basically is also another consideration. And there AI basically makes a big impact as well, because unlike the traditional solvers that kind of have to run sequentially, or even if they're run not in sequence, basically if their runs are submitted in parallel, you need either a lot of computers basically, or you need a lot of time to simulate essentially, which is more easily solved by AI, where you are actually parameterizing the model and solving the entire design space, for example, simultaneously. so that finding a particular configuration becomes a matter of inference, which goes extremely fast. So that's where I think AI actually distinguishes itself from traditional solvers.
Excellent. Thank you so much, Sanjay. When it comes to data-driven neural networks and also PINs itself, could you maybe point out the advantages but also disadvantages from data-driven neural networks? And then we'll cover PINs, which will then lead us to SimNet. Maybe start with the DDNNs.
Yeah, so the advantage of data-driven networks basically is that if you had plenty of data, it becomes like a sort of a big data problem. You don't necessarily need to know the underlying physics. If you, let's say you had a product where you put the sensors all across and you kind of just collected the data, then you could start probably predicting some behavior, provided there's enough data for that. So that's the clear advantage, that you don't need to know the underlying science, basically. The disadvantage, basically, is that if you don't have data to that scale, which is the case most of the time, then you have to actually generate the data synthetically, or basically look around for it. And once you so that time that's required for generating the data can be substantial, and that's one impediment. The second is not having any knowledge of the underlying physics actually can be even more crucial, and that can be a problem, because number one, your fidelity of the learned model basically is only as good as the solver that you use to generate the data, basically. And we all know that if you take 5 different solvers, basically they'll probably give you 5 different results, unless it's a very simple textbook type of problem. And especially nonlinear, the more the nonlinearity, the worse it gets. So the fidelity of the network basically comes in question, and then resolution of finer features basically may not necessarily always be possible. So those are the cons of data-driven network. That is exactly why researchers have invented the physics-driven networks, or science-based networks, I should say, because now you're not necessarily relying on data alone, or data at all in many cases, and you're obeying the underlying physics, basically. But the more important thing to note is the generalization. So while you still have to do the training for that class of problems that you're trying to solve, it is a lot more generalizable than a data-driven network. So that's where PINs actually have the advantage. The disadvantage of PINs is that you have to program the physics in it, and not just the physics. You have to kind of make sure that there are enough features that will make the problem converge, because that can be a significant deal, which is where we come in with SimNet. And the second possible, I would say, disadvantage is that the training does take a little bit of time. But again, if you're comparing with one single solver run neural network, basically physics-informed neural network will be slower. But that's not where one wants to use it, because then it's not as appealing. The appeal comes from the fact that you can do multiple configurations at the same time. So that's where the advantage of physics-based networks come in. And that's what SimNet is based on.
Mm-hmm. Would you say that SimNet then is kind of a hybrid or a mix between DDNNs and PINs, and tries to take the advantage of both sides? Is it true?
So PINs has the SimNet has its origins, I should say, in PINs. Mm-hmm. That's where it started out from, because I think we, having a computational background, basically, I believed in that implementation, basically, of the neural networks, and we soon we solved a large class of problems, different kind of physics. Every time we used to solve problems, we solve problems, I should say, we compare it with existing solutions just to make sure that validation is done, because that's one of the most critical things that you would want to do, especially in a developing sort of field. And so, in that sense, we have come to a point where we ended up implementing those features that are needed to solve complicated problems, industrial scale problems, that the data-driven networks basically will not be able to attempt. And where we differ from existing literature in pins is that we have introduced the special networks and features that are specific to solving those class of problems, and they are not specific to application, but generally class of problems. So that was the origin of SimNet, but we realized and we found that different kind of applications, different classes of physics require more than just that. And so you have a place where you have a combination of physics-based with data-driven networks. For example, taking a case of transient problems where you may want to run the solver up to a certain point and then have the neural network take over and do the predictions for the rest of the time. And there, you can have, RNNs or convolutional LSTMs or GRUs, basically type of networks, which can actually combine with traditional numerical techniques or pins, basically, which can do the accurate physics-based solve in the beginning, and then let the data-driven sort of network take over while it's learning when the solver is solving, whether the solver comes from AI or traditional method, that doesn't matter. So that's another interesting area, basically, where traditional methods can be combined, and then the other one is basically having numerical methods, basically, where they can be combined with either physics-based methods. For example, if you're trying to do turbulence modeling or a micromechanical modeling of composites, then yes, you can do that with traditional solver by itself, but the process is going to be so expensive that you cannot use it on a daily basis. And so neural networks can offer a good compromise where you actually train it on some fundamental problems, basically, and call it from the traditional solver. So you get the benefit of improved accuracy while not giving up the speed of the more macro, basically, algorithm, essentially. And it can also combine with again, as I mentioned before, LSTMs for transient problems. So there's all sorts of combinations as well as standalone methods that exist, and clearly, if we want to really solve a general class of problems, then I think a combination of all these would be important, and that's where we come in the picture with SimNet, where we call it a neural solver. Pins happens to be one of the methods in the toolbox, and a very important one. But there are others as well, which basically will be released in the future releases as well.
Excellent. And while you're talking about it, I'm very enthusiastic and cannot wait to get my hands on SimNet. I have everything downloaded so far, and everyone interested listening to this podcast right now with Sanjay, I will put a link to SimNet down in the description. Would you say that SimNet is a black box? Because me as an engineer, I want to see what's the underlying principles of SimNet. Can you access it somehow, or can you play with it with the layers of the network?
Great question. So actually, SimNet is anything but black box. So once someone registers on the SimNet website and downloads SimNet, they will get a complete package, which basically includes a source code, which includes the examples and all the documentation that consists of how to install and how to run the problems, which we call user guide, where many different examples are solved, showing how to use the networks. But there's also an API manual, programmer's manual, which basically goes to your question actually in terms of can you do customization yourself, and that is actually a key point actually that you touched on. So SimNet is, I would like to imagine as a community platform where everyone collaborates, and it's basically, it is a developer's dream in some ways. Let them essentially utilize the SimNet platform for their own development, because there's no sense in reinventing the wheel. And so we work with many universities, and there are, of course, lots of companies as well, but universities are more open in their technology. So if someone basically wants to implement their own method, they can do so. They can use the SimNet APIs. If something doesn't exist, we would be more than happy to work with them because eventually it'll benefit everyone. And if they would like to share their work with us, then clearly we would be more than delighted to talk to them about it. And if it makes sense and aligns basically with the rest of the vision, then we integrate that in SimNet and release to all others so that everyone benefits in the community, not just one segment or the other. And in fact, it's kind of dangerous to even think about a black box type of situation, because that's what commercial products do best in terms of UI, in terms of packaging, and so on and so forth. And while SimNet may get to the point where it becomes much easier to use as a UI, not may, it will, but that'll be more for giving users a good, easy access to solve their problem, not necessarily not know what's going on behind the scenes.
Yeah, I can't wait to get started with SimNet, Sanjay. I'm so excited. When it comes to the community itself, when someone wants to get started with SimNet, you have some basic tutorials there, whether it's, I think, spring mass system, lid-driven cavity, as well as heatsink, where you have to do some kind of inverse, determine the heat, I think some coefficients for the PDE. How big has my graphics card need to be, or do I need to have a big machine? How can I use that? Because I think some people have concerns regarding the computational power.
And that's a great question actually. So clearly the answer lies in how big a problem you want to solve. So in that sense, it's no different from a traditional solver, because you kind of know, you have a general feeling of what kind of problems you would solve, and you basically buy machines to be able to solve that problem. If you are working with 2D problems and your primary aim is as a student, a research type of setting, basically, you can get away with graphics card that are not the top of the line, basically, like A100s actually. If you want to solve industrial problems with all the bells and whistles and complexities, then clearly you are talking about a very large point cloud that basically is at the heart of the neural simulation. Unlike, so in that sense, it's somewhat parallel to a mesh, but it's not a mesh. It's just a point cloud, and so depending on the type of physics you're solving, the kind of problem you're solving, you could use easily, let's say, a multi-node DGX A100 cluster. So we have actually solved problems from the simplest, which take little time, that can be solved on let's say V100 or even Pascal basically based GPUs, but most of our problems basically that we are trying to solve are real world problems, and we recommend using at the very minimum V100s, preferably A100, just because of the features that are there in A100. For example, you have FP64, you have TensorFlow 32, so you have the ability to get more accurate result faster. So that is one of the things.
Great. Is there anything else you would like to tell the audience which they should know about? I also think you released a paper, Sanjay, right? If I'm not mistaken. I can also put that down in the description. Anything else from your side which you think the audience should know?
Yeah, no, I think the paper basically is dealing with different kind of use cases. Of course, the best source is the user guide, because we have tried to, whenever we implement a feature or area of physics, we try to come up with some sort of example, either 2D or 3D. 2D just for the purpose so that people can run quickly and check. 3D is to show the power of the product. There are plenty of different examples as you have noted yourself, and we hope to actually keep on increasing that as we go further, because I think clearly that is what we are hoping for the users to be able to take advantage of and get started and leverage SimNet in ways that basically we have not even dreamed of.
This is so cool. Sanjay, to the audience listening, I think we talked about this before the podcast. Maybe we can showcase something on my channel in the future, whether it's like a 2D problem or anything like that, to get people actually started and grow the community, because I have a lot of people contacting me on LinkedIn saying, hey, how can you combine AI with engineering? And I think this is an excellent way to get started with pins or just delve into this exciting field. I would thank you so much, Sanjay, for your time today. And I hope there will be a second part where we can talk about more advanced, let's say, developments of SimNet.
Happy to be happy to join again at some point in the future.
Awesome. Thank you so much for your time, and I wish you a great weekend.
Thank you. You too. Take care.